Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, we are very happy to have Adams Wei Yu from CMU. Adam is a PhD student at CMU, and he did a summer internship last year. Today, he will talk about something different from his intern work.
Okay. Thanks for the introduction. So I'm Adams from CMU. Today, I will introduce a very efficient Doubly Stochastic Primal-Dual algorithm for empirical risk minimization problem. And this is a joint work with Qihang Lin and Tianbao Yang. They are both from University of UIowa. Okay, so a lot of machine learning problems can be abstracted to the following empirical risk minimization problem. It is essentially minimizing a convex objective which contains two parts. The first part is called the empirical loss, which is computed from the given data. And the second part is called the convex regularization function. For example, it can be the L1 norm, L2 norm, which can be incorporated our prior knowledge on the decision variable. And we further assume that the loss can be decomposed as the summation of the different loss on different data. Okay, so if the loss is a square loss, then it will be a linear regression problem. And if the loss is a sigmoid function, then it is a logistic regression. If the loss is a smooth hinge loss, then it will be a smooth SVM. Okay, so it indeed captures a lot of problems in the machine learning community. And we have the following assumption on the problem. The first is that the regularization G can have a decomposed structure, which is a summation of the different coordinates. And we also assume that each Gj is lambda strongly convex. And we also assume that the loss function phi I is 1 over gamma smooth. Okay, this is all our assumption. And if we introduce the functional conjugate of the loss function, which is the phi I star, then we can reformulate the original empirical risk minimization problem as the bilinear set upon problem, which we will introduce a new term, which is the bilinear set upon. And this A is the data matrix with each row is a data. And it is in each data is of dimension P. Okay, so in the following, we will work on this formulation rather than the original formulation. Actually, there is a lot of various work on this empirical risk minimization problem. There are two lines basically. The first line is called the stochastic gradient method. Actually, in each iteration, such kind of methods use a stochastic gradient which in expectation is the same as the full gradient, but they will have a variance. The algorithm include the proposed by the following authors. And another line algorithm is called the stochastic variance reduced gradient method. This method introduces a new term and subtract another term, such that the stochastic gradient is still have the same expectation as the full gradient, but it has a lower variance. So this is called the stochastic variance reduction. Okay. Another line of algorithm is called coordinate methods, which in each iteration they just sample randomize select a few coordinate and do the coordinate descent. This line of algorithm is not accelerated, but this line is accelerated, which means that they have a square root dependence of the condition number kappa. Recently, there is some algorithm proposed on a Primal-Dual algorithm, which they work on the set upon formulation. Okay. So all of these algorithms assume that the number of data n is huge, but the dimension p is relatively small. So all of them just focus on sample 1 or a batch of data point in each iteration. Okay. Yeah, Chung has a paper in NIPS 2013.
It was different from most of the HGD therapies.
Yeah. But basically, the general idea would be the same.
The idea is the same, but the formulated is very different.
Yeah.
Who is a
Qu, do you know?
This is a postdoc with Peter Sparks.
Yeah, she also worked with Tong Zhang. Currently, she is an assistant professor in the University of Hong Kong. Okay. So, yeah, but what if when P is relatively larger than N, which will happen in the high dimensional space case. And in that case, we can just simply sample one or a batch of feature in each iteration and apply the dual version of the approaches mentioned above. But what if both N and P would be large? A natural solution is just to sample one data point and one feature in each iteration. There are few previous work on this line, and this talk we also fall in this category. Okay. In this talk, we will care about and answer the following questions. The first is that what is the iteration complexity of a coordinate method for problem that we can sample both from the primal and dual spaces per iteration? It is essentially to answer what is the convergence upper bound of the algorithm. The second question is, when would this type of algorithm would be better than the purely primal or purely dual coordinate methods? And this will be concerned about the overall complexity of the algorithm. The third question is, what's the fundamental limit of this type of algorithm? And this is essentially the convergence lower bound of this type of algorithm. Okay, so we will first answer the first question by proposing new algorithm. Okay, so let's quickly review the problem. We would like to solve this empirical risk minimization problem, and we formulate it as a set upon problem. And A sub I is the ith row of data, and AJ is the jth column of the data. Okay. Now let me review one very famous algorithm, which is proposed by Yuchen Zhang and Lin Xiao in 2015.
It's already famous?
I think so. I think it's famous because it collected a lot of citations. And okay. And okay, the idea is as follows. In each iteration, the algorithm sample a subset of data points, which the number of data points would be m. And first, they do and use this n data point to do a dual update. This y is the dual variable. Okay, so if it is if the data is sampled, then update the corresponding dual variable, and if not, then remain unchanged. And then we do a momentum update of this dual variable. Okay, after that, we use this updated dual variable to update the primal variable. But in this step, they do a full primal update, which means that they update the full vector of x. Okay. And then again, they use the momentum update. Okay, this is basically the SPDC. And in their paper, they show that if they choose a proper step size, then their convergence rate would look like this, which has a dependence on the log 1 over epsilon, which means that their convergence rate is linear, and their convergence on their dependence on the condition number kappa is square root, which means that they are accelerated algorithm. And this condition number is defined as the maximum L2 norm of the data over the strongly convex and smooth parameter. Okay, it illustrates how ill-posedness of the problem. Normally, lambda and gamma would be small. Then the kappa would be very huge. So they have a square root of this kappa, which means that they are low. The complexity is relatively low. Okay, so this is basically the theoretical result of SPDC. And the overall complexity of SPDC is just nothing but the number of iteration times the per iteration cost. Since their per iteration cost is MP, M is the number of sample from the data, and P is the dimension of the data. It is due to the inner product. So the overall complexity would look like this. But what if we sample both from the data and features? This is what we propose, the Doubly Stochastic Primal-Dual coordinate method, which is the short term is DSPDC. The only difference is that in the primal update, we select one coordinate to update rather than to do the full update. And also the step size and this momentum step size will be rather different. This is our result. After choosing this step size tau and sigma, to ensure this gap to be smaller than epsilon, our DSPDC needs such iteration number. Okay. Again, it is the dependence on epsilon is log 1 over epsilon, which means that it is a linear convergence algorithm. But we have some other additional term here. Now, in the following, I will discuss the difference between these two algorithms. Okay. First of all, we need to introduce the capital lambda QM, which is essentially the largest L2 norm of the block of data. Suppose we divided the data into M times Q block, and this lambda is just the largest L2 norm of the block. Okay, so now we will connect this term to the previous condition number kappa. If the data is dense and evenly distributed and has evenly distributed features, then this term is approximated like this. Okay, and in that case, the DSPDC would require this number of iterations. Our result is interesting. If the Q equals P and M equals to 1, which means that we do not do the primal sample, which means that we do the full primal update. Then it will recover this optimal rate of SPDC and the accelerated SDCA. And if Q equals to 1 and M equals to M, which means that we do not do the dual sampling and do the dual full update. Then it will recover the optimal rate by Qihang Lin's paper. Okay, so that means our result captures the previous result.
So is that assembly paper Qihang Lin, the one that this one? Yeah.
Yeah, I think it's the one with you.
With draws only.
Yeah,
Okay.
I think so. Okay, so now for the following discussion, we will assume that the M over the ratio of the primal sampling is larger than the dual sampling. Oh, sorry, the dual sampling is larger than the ratio of the primal sampling without loss of generality. Otherwise, we can just apply the dual version of the DSPDC.
So here I think we better to explain. N is a number of samples.
Yeah.
M is the mini batch. So
Yes, yes.
P is the number of dimension of parameters.
Yeah.
Feature. The Q is the like a start block of the feature you use.
Yeah.
So it's like both is the full batch, batch size versus the mini batch ratio.
Yes.
Yeah. So M and Q can, yeah. So M and Q can both be 1.
Yeah.
Basically, you just pick one example or one feature, then you will be N and P left. But you can use mini batch or block coordinates, then that will become a ratio. Yeah, I think that's the most important part.
Yeah.
Cool.
Yeah. So, yeah, exactly. So if P equals to Q, which means that we do the full primal update, then the rate will reduce to this one, which is nearly optimal for the dual coordinate method. The optimality is proved by Ali Agawa and Liu Batu last year. Okay.
Lan Guanghui's paper.
Yeah.
He has probably a better proof.
And correct proof.
Yeah, correct proof.
Yes. Yeah. And if N equals to M, which means that we do not do the sampling from the dual, then it becomes this, and which is very likely to be optimal. But no one has proved this at this moment.
So very likely you have win from empirical results.
Likely means that we do not see how can we accelerate this. That's why we call it's likely to be optimal.
Okay, so the asymmetric part is you do not have the square root, right? If you compare this one to the first one, you have square root kappa times square root n divided by n.
Because we assume this one is larger than this.
Okay.
That means this part only have the n over m, and if it is equal, then it would be 1, right? Actually, n equals to m, and this ratio larger than this implies p equals to q.
Yeah, but it's not symmetric. Still not symmetric.
If it's p equals to q, then actually this should be 1, right?
No, I know. It's not p and q. Just assume the ratio is the same, okay?
The ratio is the same?
Suppose n divided by m equals to p divided by q.
Yes.
Now it could be 10, for example,
Okay.
or even 100.
Okay.
And then your complexity, the word will be
Symmetric.
bottom.
It's also symmetric.
They have this square root. You don't have a square root over p and q.
PQ, because you assume that P over N over M equals to P over Q, right? So then this would be also equals to N over M.
Yeah,
right.
Look at the first one.
This one?
Above, you have a square root of n divided by.
Which one?
That's just one line above.
This one?
The second.
This one?
Yeah.
Okay.
You have square. Just look at the coefficient of the kappa, square root of kappa.
Okay.
You have square root of n.
If P equal to Q, yes, then this we can.
No, don't look at that. Just look at that.
Okay.
You get the square root of kappa, square root of n over m, right?
Yes.
And the next one, you
The
get
next one?
square root kappa p over q. If for symmetric, I would imagine that square root of p and q times kappa.
Yes.
Oh, okay. You
But
have
this
if
is-
n equals to n. Okay. If,
Yeah.
Okay.
We have additional assumption. I mean, actually, they would be symmetric if you.
Okay.
Yeah. Okay, so this is a comparison between the SPDC and the SPDC. For this part, for the second part, they are same except that the SPDC has additional factor P over Q, and this part would have additional P over Q. If P equals to Q, then it exactly recovered the SPDC's convergence rate. Okay, but on the other hand, it shows that the SPDC has a slower convergence rate because P is always larger than or equal to Q. So this term is always larger than this term, and this term is always larger than this term. So, but that makes sense because in SPDC they do the full coordinate update, but we just sample. That means we need more iterations to converge to the same epsilon. Okay, so that means the SPDC in terms of convergence rate, the SPDC is lower than SPDC. And for the per iteration cost, SPDC has m times p, but the SPDC also has m times p. That means the overall complexity of the SPDC is this. It is still slower than SPDC.
That's higher.
Yeah, slower.
Oh, slower. Okay.
Slower. Yeah. Yeah. Because the SPDC have additional P over Q term here. So P is over. Yeah.
Yeah, P over larger than.
Yeah. That means in general, the SPDC is slower than SPDC. Okay? So that may not be a good news. So that will make us to ask when will the DSPDC as some advantage over the SPDC, right? So in the following, we will consider two cases in which in these cases DSPDC is better than SPDC. The first scenario is when the data is factorized, which means that the data A can be represented as a multiplication of two matrices. One is U and the other is V. U is the N times D, M by D matrix, and V is the D by P matrix. And D is much smaller than the minimum of N and P. And this type of factorized data can be always obtained, for example, by the singular value decomposition or non-negative matrix factorization or randomized matrix approximation and some randomized data feature reduction. And it is often used as a pre-processing step before training a statistical model to reduce the noise and also to speed up the training. Okay, so now the A is represented by the multiplication of a very tall matrix and a very fat matrix. Okay, so now to be this is in this case we want to build a prediction model in the reduced low dimension space using this U. And consider that the original model is AI times X, and the reduced model is just the UI times X hat. Okay, but the reduced model can be learned faster, but it's a little bit harder to explain because we already project the data to a lower dimension space. And it is also harder to use for subsequent analysis, such as the predicting new instance and feature selection. So this is a trade-off. This is a computational and explanation trade-off. Okay, the factorized data model can be also formulated as follows. This is the original model, and after that, after do the data dimension reduction, then it will become this. And now the factorized data is the U times V, just as we mentioned before. Okay, so when we work with such factorized data, we can see some positive point and negative point. For example, we check the quality of the data for factorized structure. And the structure should accelerate all the optimization algorithm for the ERM. However, for different algorithm, the benefit from the factorized structure is to different extents, which we will explain in the following table. Now we will maybe skip the detail of how we implement this. The message is that for the factorized data, the per iteration cost of the SPDC as dm times dq, which is much slower than MP, because d is much smaller than the maximum n MP. Okay. And this is the implementation detail, and we just need to maintain a U bar and a V bar additionally to make it feasible. Now this is the comparison between the SPDC and the other algorithm on the factorized data. This column is the number of iterations. We can see that in this case, we assume that m equals to q equals to 1, which means that in each iteration we only sample one data and one feature. So the number of iteration, the DSPD is larger than the SPDC, and also larger than the ASDCA. But the cost per iteration, DSPDC is the smallest. So the overall complexity, DSPDC is the smallest by a factor of p. Okay.
That's only when the first term dominates.
Yes. So especially when n is large, then the first term will be dominant. Okay. So, yes. So we can see that for the factorized data scenario, DSPDC indeed is faster than the competing competitor. Now we will talk about the second scenario, which is called a matrix risk minimization. In this case, the decision variable x is a matrix. And this x matrix is decomposed to p blocks. Each block is a d by d matrix. And now the formulation is almost the same as the vector version, except that the inner product is replaced by the Chase norm, and the outer norm is replaced by the Fabrice norm. Okay, so there is a lot of applications of this formulation, such as the matrix Chase regression and distance metric learning. But for this scenario, for most of the scenario, we need to impose additional constraint such that each block of this decision variable is semi-definitely positive. Okay, that will pose a computational challenge. That is, for each iteration, we need to project the variable x to the PSD con. So we need to do an eigenvalue decomposition per iteration. which has complexity is qubit of D. Okay. Now we'll skip most of the detail and just show the theoretical result. For this matrix minimization, the number of iterations is the same, but we only need to do one eigenvalue decomposition per iteration. But all the other competitors need to do P eigenvalue decomposition. So the overall complexity, the SPDC again wins. Okay. So again, the advantage consists in the first term compared to the SPDC. And actually, in practical scenario, the SPDC is much faster. And the reason is, although the number of iterations looks like larger than SPDC, however, all of these are upper bound, which means that they might be loose. But the cost per iteration is concrete, which means that for each iteration, the SPDC indeed saves P times computation. So the practical time saving by the SPDC is more significant, and we will see in the experiment. Now we will show some empirical study. The first is on the factorized data. In this case, we choose the loss to be the smooth hinge loss, and we generate the data as the following, which I will skip. So we compare our algorithm with SDCA and SPDC, and in terms of the number of arithmetic operations, we can see that the SPDC is faster than the two state-of-the-art competitors. Okay.
What is y-axis?
The y-axis is this one. This is the objective value. Yeah, the primal objective. Okay. This is the primal objective gap. Okay.
I think for this conversion, you are using probably a non-careful implementation of SPDC.
Why?
Because with L1 or L2, there's a full vector operation in SPDC, right?
Yes.
But you can make it the same as SDC.
SDCA?
Yeah. So per iteration will be same cost SDC, maybe times 2. Basically,
Okay.
there's no full vector update at all. It's all sparse update.
Yeah, we also use we also use this update. I mean, we use because it works on the factorized data.
Okay, factorized data.
Yeah, it's factorized data, not the original formulation.
Yeah, because I think in the original formulation, SPDC will be faster than SDC.
Yeah. In the original, I think SPDC would be the fastest. And okay. And we also use the lambda equals to 10 to the minus 2, which means that the kappa is not that large. Okay. But even for the small lambda, which means that the kappa is large, the SPDC is still comparable with SPDC, and actually it's a little bit faster. Yeah. And SDC is the slowest. Okay. As for the real data, we run out the 3 algorithms on 3 real data sets, the curve type, the RCV1, and real sim, and we manually project the original data to a low dimension space, which only contains 20 features, and we choose the sparse lambda 1 would be 10 to the minus 4, and the L2 lambda 2 would be 10 to the minus 2. Okay. Again, we can see that the SPDC outperformed the other two competitors. Okay. The second experiment is on the matrix risk minimization, and we generate the data as following.
For the previous study, do you also compress the time directly? Just compress time?
That's a good question. So actually, if compared with time, that SPDC might be a little bit slower. It depends on the implementation. Because, as I mentioned, the SPDC use more iterations. And if you implement it on MATLAB, for example, you need much more for loop. And then it would be much more slower. Yeah. So we show the arithmetic operation just for the sake of fair. In that case, it would be much more fair, independent of how you implement this.
It's not fair is because, in the sense that it depends on how much your numerical computing can be parallelized.
Yeah.
For example,
so,
yeah, if that's direct translate in the time.
Yeah, in our case, we just enforce they use a single thread computation. Okay. In this matrix risk minimization, each variable, the ground truth variable is chosen as the D by D identity matrix, and there are P such kind of identity matrix. So in this case, we again choose the smooth hinge loss. We assume that the D is 200 and the P, which means that the number of the block of this D by D matrix is 100. And we sample 100 data point, and the lambda is set to 0.01. So, as we mentioned before, the SPDC in this scenario is even faster and more significantly faster than the other two competitors under different sample schemes. No matter M is larger than Q, M equals to Q, or M is smaller than Q. Okay, that's basically because in each iteration, we only need one eigenvalue decomposition, but the other two competitors need P eigenvalue decomposition. And that saving of time is very significant. Okay. So this answers the second question. That is when the DSPDC would be much more efficient. We give two scenarios. Now the third question is, what's the fundamental limitation of this type of algorithm? To answer these questions, first we need to formally define what's this kind of algorithm. It is basically like in each iteration we restrict, we can only sample one coordinate and one data, and then we can add the points to the current solution, which is just the linear span of either this point or its gradient, or the inner product between the data block and this point. And we do it again we do it both for primal and dual. And this is the abstract description of this type of doubly randomized coordinate algorithm. Now, in the following, we will give a bad case to show that this algorithm would need, at least how many iterations this algorithm would need to solve that problem. The bad case is a conjugate function, both for the primal and for the dual. And the data we generate is we use is very sparse. It's just look like a diagonal matrix. Okay, in this case, we also assume that the number of dimension is the same as the number of data. Okay, which means n equals to q. Now we can easily compute the parameter that is necessary. For example, the lambda, the gamma, and qm. And by the theorem of the SPDC, it would need this number of iteration to make it converge to the optimal solution. And on the other hand, because this formulation is conjugate, we have a closed form solution. It's as simple as this, and just a few lines of linear algebra. Now we'll discuss about why this case is bad for this type of algorithm. The first observation is that the closed form, the optimal solution has non-zero entries, both for the primal and for the dual. Okay, but for the algorithm we consider, only when there is one primal dual interlaced in the sampling sequence could add one non-zero entry to both primal and dual solution. But this is a very rare event. That means that only after a lot of iteration can we increase one non-zero entry to the solution. Now, this is an example of the sample sequence, and I will explain what is the interlace. So each bracket is a primal and dual indices that is sample. And this is for the iteration 1, this is for the iteration 2, and so on and so forth. And only when we first sample one index in the primal, and later on we sample another index in the dual, and they coincide with this one, can we increase one non-zero of the solution? And we prove that's non-trivial. We show the probability that how can we get this, and there would be that's a very rare event. And we will skip the technical detail here, and we will show the result as follows. So suppose if we apply any algorithm of this type to the set upon problem 1, and the output is xt and yt, then to make sure that the primal dual gap is more than epsilon, we need such number of iteration to make it converge. Okay. So compare with our upper bound. Unfortunately, we show that our bound is not tight by a number by an n factor. If n is more, then it would be almost the same. But if n is large, the gap is still large. So there is an open question: is can we close the gap? Our conjecture is that the upper bound cannot be tighter, but maybe we can give a worst case to make this lower bound tighter. Okay, so this answers the third question: what's the fundamental limitation of this type of algorithm?
How do you know the UIowa is tight?
Just conjecture, because when we construct this case, we feel that we can still find space to make it worse. So actually, in this case, on average, we need to sample n times to increase one non-zero component of the solution. Actually, we think that if we can only after we sample n square time, n squared times, we can increase the number of non-zero, then this will be tight. So, and we think that's possible. So, yeah. Okay. So that's a remaining open question. So I remember that in Ale Agrawal's paper, that their lower bound is the bound of SPDC and their lower bound is still have some gap, right? The square root of n or something.
So if you read last paper has closed.
Okay.
Yeah.
I see.
So this is exact.
Okay. Okay. The take-home message of this talk is that we propose a doubly stochastic primal-dual coordinate method for the empirical risk minimization problem. And this algorithm has a linear convergence rate, and it has the lowest overall complexity when we apply to the factorized data scenario or to the matrix risk minimization scenario. So we also give a lower bound on the iteration complexity for the class of primal-dual stochastic coordinate methods. And there is an open problem remain, that is, can we close the gap between the lower bound and the proposed upper bound? And thanks.
Great talk.
Thank you. So,
more slides, looks like.
So
okay, reference.
Oh.
About the outbound low-bound issue. So you don't think about its algorithm issue. Because there are three different factors.
Yeah.
Either the algorithm is not optimal, or the bound is not optimal, or the low bound has some problem. There's three factors.
Yeah, actually we have, for this theoretical result, I mean for the upper bound, we have proved this almost 1 year ago. And to think about the lower bound, we also think for a few months. And our intuition is just as what I mentioned. I think that the case could be worse. Why the gap? I mean, the lower bound cannot be, improved because for the SPDC is optimal, right?
Yeah, that's optimal.
So our conjecture, the SPDC would be also optimal. We have no base to improve. Right. This is our intuition.
So our side is exactly the same, right?
Yeah.
Yeah, I think the upper bound looks more safe for me, but more tighter, easy to be the tight one. But the lower bound can be good. That's what I'm saying. Same thing.
Yeah. Actually, our original, we want to sample one. Okay, when we sample, there is one interlace that would be increased by 1, the non-zero. Actually, I think it would be 1 over n squared, but our computation shows that it's just 1 over n. That's why, yeah. So we have finished this for a while, but we did not submit it because we want to close the gap, but we didn't manage to do that at this moment. Yeah.
Total each. Close the gap.
Qihang told me that they think Alec Agore's bound is not good, but Alec Agore is afraid he's going to go recording. Oh yeah, it's recording.
Okay.
Yeah. So that's okay. Yeah. So usually we have some idea to improve that.
Which bound?
That's the
lower bound.
Yeah.
But Lan has already finished.
Yeah. But somehow he seems Lan's proof also has a problem. Which I don't
because
know.
Lan's what he adjusts is a little bit, easier than Agora's. Agora, the lower bound that it covers is on a more general class of algorithm. Lan only focuses on a small class of algorithm. That's why it's easier to achieve. Yeah.
So you may also try to your algorithm more using that. That is C++.
Yeah, we Actually, we try to. But we translate the MATLAB code to C++. But in terms of time, it might not be faster. But I mean, for the matrix case, it would be faster because we save a lot of time in doing the eigenvalue decomposition, no matter MATLAB or C++.
So actually, my question, if you use a C++ to implement and then to follow the issue as in MATLAB, you can compare the exact time for different operators.
Yeah, it is a good suggestion.
Great.
Okay. Thanks.